Dear listeners, in our previous lecture, we discussed the methods which are used for determination of surface and interfacial tension. We spoke regarding 4 different methods: capillary rise method, drop formation method, ring detachment method, and bubble pressure method. All these methods are used for determination of surface tension, and drop formation method is that which is being used not only for determination of surface tension but also for determination of interfacial tension. Now we wish to move on to the another important concept in surface and interfacial phenomenon, and that is spreading coefficient. We want to discuss about spreading coefficient as there are n number of processes in pharmaceutical industries where 2 different phases come together during either mixing or different processing, and how will they behave with each other, how interfacial tension will play an important role in giving us the uniform formulation. That all depends upon the concept of spreading, whether the adhesive forces of attraction between those 2 phases will be greater than the cohesive forces of attraction between their own molecules will decide whether spreading will take place properly or not. And hence, we wish to discuss about spreading coefficient today. This concept is also important when we go for preparation of emulsion and suspension, as well as when we are going for application of topical preparation onto the skin. Preparation of emulsion will have interaction between internal and external phase, and being these are 2 immiscible liquids which we are trying to mix, the interfacial tension will be very high, and emulsifying agent will be playing an important role in reducing that interfacial tension and encouraging the mixing of external and internal phase. Similarly, in case of preparation of suspension, how the interaction between solid which is insoluble in the given solvent will be increased with the help of suspending agent. There also, the interfacial tension between solid surface and liquid molecule can be decreased with the help of suspending agent. In case of application of topical preparation, whether topical formulation will spread uniformly onto the surface of the skin or not, that all depends upon how the molecules of the formulation develop adhesive forces of attraction with the molecules onto the skin and spread uniformly. So let us talk about spreading coefficient. Say when we are trying to put oleic acid onto the surface of water, it forms a uniform film, and this formation of film is because the forces of attraction between the molecules of oleic acid and water, that is adhesive forces of attraction, they are greater than the cohesive forces of attraction between the oleic acid molecule. If it is not so, then the added molecule or added material will never be able to form a film onto the surface of sublayer liquid. So, if we want to understand this in terms of how much work we will have to carry 2 molecules of the spreading liquid from the molecules of sublayer liquid, we can understand it by knowing the work of adhesion which we will have to carry out. The work of adhesion is required to break the attraction forces between unlike molecules and is being obtained with reference to the figure Say for example, we are considering the two hypothetical cylinders. The upper part of the cylinder is spreading liquid and lower part of the cylinder represent the sublayer liquid. Now we know that surface or interfacial work which we will have to carry out to separate these two molecules or two layers, we will have to work against surface tension multiplied by the area which is being increased. So, see, these are two hypothetical cylinders. The surface area of the cylinder is 1 centimeter square. When spreading liquid and sublayer liquid, when these molecules are in contact with each other, they have interfacial tension represented by, say, YSL. Now we are breaking down the interfacial tension and separating spreading and sublayer liquid. So while doing this, we are creating two different surfaces with two new surface tension, that is YL and YS. So total work of adhesion which is being done by us is we have created two new surface tensions, YL and YS, breaking down the interfacial tension which was existing between spreading liquid and sublayer liquid. So the work which is being required to separate these two molecules of two different liquids is work of adhesion, and this can be given by the equation WA is equal to YL plus YS. YL plus YS is nothing but these are two different surface tensions which are being created of new two surfaces, breaking down the interfacial tension between spreading liquid and sublayer liquid. So WA is equal to YL plus YS minus YLS. Now let us understand the work of cohesion which exists when we are trying to separate the molecules of the spreading liquid from each other. Because unless and until molecules of the spreading liquid are ready to break the bonds or to have minimum forces of attraction between themselves, it won't be possible for us to spread the spreading liquid onto the sublayer liquid. So the work of cohesion, it is the force which will be required to separate the molecules of the spreading liquid so that it can flow over the sublayer liquid, forming the film over it. Again, we can understand this with reference to the figure. Now, in this case, we have only spreading liquid molecules and we want to separate them. We will be creating two new surfaces with surface tension of YL each. So work of cohesion will be given. No interfacial tension exists between the like molecules, and hence when we are carrying out some work for separating these like molecules, which is known as work of cohesion, will be equal to 2YL. These are the two new surface tensions which are being created by separating the spreading liquid molecules from each other. Now, spreading occurs if the work of adhesion is greater than the work of cohesion. So the term WA minus WC, it is known as the spreading coefficient, and spreading will only occur if the value of S is found to be positive. if we are not finding that S is positive, that is S is observed to be negative, that time you will find that the material which we are trying to spread onto the sublayer liquid will remain in the form of drops or globules and will never form the film onto the surface. So final equation for spreading coefficient S is equal to WA minus WC. We have determined the values of work of adhesion as well as work of cohesion. Putting those values into the equation and rearranging equation, we come up with equation S is equal to YS minus YL minus YLS. Rearranging and simplifying the equation, we come up with the final equation S is equal to YS minus in bracket YL plus YLS. So if we want that spreading liquid should spread over sublayer liquid uniformly, forming a film or ring, then for sure we need to have the surface tension of sublayer liquid higher than the surface tension of the spreading liquid and the interfacial tension that exists between spreading and sublayer liquid. So if S is positive, that is when the surface tension of sublayer liquid is greater than the surface tension of the spreading liquid along with the sublayer and spreading liquid. If YL plus YLS, if it is larger than the surface tension of a spreading sublayer liquid, the substance forms globules or floating lanes and fails to spread over the surface. So if the second term into the equation, if it happens to be greater than the surface tension of the sublayer liquid, then for sure value of S will be negative and the spreading liquid will not be able to spread onto the sublayer liquid, and hence it will form a floating lanes or globules onto the sublayer liquid. Spreading can also be taught in terms of the surface free energy, because we have seen what surface free energy is. Surface free energy W is being given by equation surface tension multiplied by area increment. Here we are talking about 1 centimeter square area. So the added substance will spread if it reduces the surface free energy of the system. So in another way, we can say that if the surface free energy of the new surface and the new interface, if it is less than the surface free energy of the old surfaces, then and then only spreading will take place. So if we observe that adhesive forces of attraction are greater between the spreading and sublayer liquid, then for sure spreading will be uniform and the interaction which is taking place between those two phases will be excellent. Say for example, we are going for mixing or application of the topical formulation, it will be uniform. This was all about the spreading coefficient concept. Thank you. Thank you very much. In the next lecture, we'll start talking about adsorption at liquid interfaces. We'll be talking about positive and negative adsorption. We'll be seeing the materials which exhibit positive adsorption, and these are really fascinating molecules which comes to the rescue of pharmaceutical formulator and they are known as surface active agents. So we'll deal with surface active agents in detail in our next lecture. Thank you.